This
topic.
conference will now be recorded. This conference will now be recorded.
Now, this presents what is decision making in operations management. An operating system utilizes resources to convert inputs into outputs in the form of goods or service. Conventionally, operations management is defined as the task of designing, establishing, planning, running, controlling, maintaining, and improving such systems. Now, the strategic operation management decisions, the areas in which important decisions need to be taken: goods and services, quality management, process and capacity design, location, layout design and strategy, human resources and job design, supply chain management, inventory, scheduling, maintenance. I am not going into detail. I shall focus only on techniques with some specific problems. Now, the main theme is decision making. What is decision making? Decision making is the task of selecting the best alternative amongst available candidate alternatives with respect to a particular or a set of criteria. Sometimes we can call criteria and attribute as synonymous. So either you can call criteria or attribute. Now, decision making is the task of selecting the best alternative from amongst a set of available candidate alternatives, in which each alternative is evaluated or assessed by some criteria, maybe a single criteria, maybe multi criteria. If it is single criteria or attribute, it is called single criterion or single attribute decision making. If the scenario is to decide based on multiple attribute or multi criteria, it will be called multi criteria decision making. Giving you an example, say an interview is going on. The expert panel evaluates the efficacy of the candidates, and each candidate is evaluated by a set of criteria. So the candidate applicants are nothing but available alternative, and the task is, from amongst that alternative, you have to select the best applicant, or you can rank the alternatives, rank the candidates based on their interview performance. And each candidate is evaluated by a set of criteria or attribute. For example, 10 standard mark, for example 10 plus 2 mark, for example degree of efficiency in communication skill, for example attitude. So these are some criteria. Now, single criterion decision making is very simple, whilst problem arises in dealing with multiple criteria which are contradicting in nature. Now, here comes one concept: criteria conflict or attribute conflict. Single criterion decision making is very simple. By evaluating or assessing the values, you can select the best or rank the candidate alternative by means of their performance. Okay, but when multiple criteria come into picture, the problem is sometimes criteria are contradicting in nature or conflicting in nature. Then question arises, what is criteria conflict or criteria contradiction? Now, there are some criteria whose higher values are always preferred, and some criteria whose lower values are always preferred. For example, in a robot selection problem, load carrying capacity of a robot, it should be higher is better, as high as possible. At the same time, cost of the robot should be as less as possible. So that is, lower is better. So when there is criteria conflict, it is very difficult to select the best candidate, best alternative. Okay, so there are some techniques how to take care of that, how to decide, how to solve a multi-attribute decision making technique, that we shall discuss. Now, this figure shows an example of decision making matrix in which each row represents criteria values of a particular alternative and each column represents alternative values corresponding to a particular criteria. If you follow the nomenclature x11, x12, x1n, 1, the first one means alternative 1, and the second one 1 2 up to n, this means n different criteria c1 c2 up to cn. So first row represents values of alternative a1 for different criteria c1 c2 up to cn respectively. Second row represents criteria values of alternative 2, that is A2, for criteria 1, 2, 3, 4 up to n respectively. So column represents a particular criteria and corresponding this criteria different alternative values, and row represents for a particular alternative what are the different criteria value. So this is called decision making matrix or multi criteria decision making matrix. Now multi criteria decision making are of two types. One is multi-attribute decision making. One is called multi-objective decision making. Some thin line difference is there. When multi-attribute decision making, decision space is discrete. But when is in multi-objective decision making, decision space is continuous. Let me give you an example in a production context. I mean, say you might have seen regulator of old fan. This regulator has 5 different positions.
How it is possible, sir? Overcoming it is possible. How is that possible? But because our experience
Sir, is I am audible? Hello? Hello?
Hello.
Hello?
Sir. Sorry,
Yes, sir,
sorry, sorry.
audible, sir.
Okay, okay. So screen is visible, no?
Yes, sir, visible, sir.
Okay, okay. So I was talking about old regulator of a fan. Fan has five different positions. Each position corresponds to a particular RPM. Okay, speed of the fan spindle. So first position 1 represents the smallest RPM value, then it increases. Position 2, position 3, 4 and 5 is the highest. So 200, say 200 RPM, 300, 400, 500, 600 RPM. Okay, 5 discrete values are there, but in between these two, 200 to 300, no value is possible, or we cannot set any value in between these. So this is called discrete decision space. Out of these 5, we have to select one. If provision is there, we can change any value starting from minimum value to maximum value. This is called decision space is continuous. Any RPM value you can set, say 200.2, 200.5, 300, 360, 340, any value you can set. So if decision set is continuous, we can have infinite number of available candidates, and out of which you have to select the best or the most alternative, so most appropriate alternative. So this is the difference between multi-attribute decision making and multi-objective decision making. Now comes decision making data. In order to execute the task of decision making, we have to deal with some data. So what is the type of data? Decision making data are of two types. One is qualitative data or subjective data, and second one is quantitative data or objective data. Now, qualitative data deals with description. Data cannot be observed, but not data can be observed but not measured. For example, color, texture, smell, taste, etc. So these are qualitative. We cannot measure these data by some exact numeric score. Okay. And second one is quantitative data deals with number and can be measured. For example, let's say number of participants in the FDP program, the value can be quantifiable. Now, number of customer acceptance in market for a particular product, that value can be quantifiable. Number of employee, turnover of a company per year, that value can be quantifiable. So these are called quantifiable data or objective data. For example, in product context, it is length, height, area, volume, weight, speed, etc. Now this figure represents data, qualitative, quantitative. Qualitative, it was great fun, but the extent of fun that you cannot quantify, you cannot measure. On the other hand, quantitative data can be measured. Quantitative data are of two types. One is discrete, one is continuous. You can see 5 is discrete and continuous is 3.265 dot dot dot. Okay, so next figure represents example of qualitative data. As qualitative data cannot be measured by numeric score, we have to assess the data or suitability of data by some linguistic term. For example, like easy, awkward, slow, efficient, ambiguous, how, confusing, like that. But in case of quantitative data, that is measurable. Now, tackling with objective data or quantitative data is very easy. So, multi-criteria decision-making tools, the variety of techniques are there to deal with multi-criteria decision-making involving objective data or quantitative data. But problem arises while data is subjective in nature or qualitative. Now, what are the challenges to deal with subjective data? One is ambiguity and second one is vagueness. Ambiguity means one in many. For example, I invite you to meet me in the institute, but it is not specified the meeting place. I have not specified where you can find me, in the department, in my quarter, in the institute canteen, institute dispensary. It is not specified. So that means probability of getting myself is many. So that is called one in many. So subjective data is ambiguous in nature, and at the same time vagueness. Vagueness means representation is vague. I say the food is sweet, but I have not specified to what extent it is sweet. Is it as sweet as apple or is it as sweet as a chocolate? It is not specified. So this is called vagueness, or we call subjective data is full of ambiguity and vagueness. If data is this such type, it is very difficult to judge or make a rational decision. It is very difficult, but it can be possible. Now, subjective human judgment, so we have to go for human judgment. Okay, experts or decision makers give their judgment, and in some linguistic term which may vary from person to person. perception of the decision maker. Okay, and that is why the data bears some sorts of incompleteness, inconsistency, as well as imprecision in the decision making. For example, if I want to evaluate the performance of a faculty, what are the criteria? For example, sincerity, dedication, these you cannot measure. So these have to be assessed by means of some linguistic term. For example, very good, good, excellent, poor, very poor, like that. But as per my understanding, if I judge somebody and give a rating poor, you may give very poor, because my perception may be different from your perception. So here comes another concept, the risk bearing attitude of the decision maker. Understand, decision maker, there are three types of decision maker. One is optimistic decision maker, one is neutral decision maker, one is pessimistic decision maker. Optimistic decision maker always assess in higher side, and pessimistic decision maker lower side, and neutral decision maker in between these two. That is another challenge to solve multi criteria decision making problem involving subjective data. Not only nature of data, ambiguity, vagueness, imprecision, incompleteness, decision maker risk bearing attitude also comes into picture, that has to be taken care of. Now comes MCDM, multi-criteria decision-making problem with objective data. Here I shall quote one example of material selection. Okay, material selection is a step in the process of designing any physical object. In the context of product design, the main goal of material selection is to minimize cost while meeting product performance goals. Cost is one of the criteria or attribute to be considered. At the same time, product performance features need to be satisfied. So the problem is multi-criteria decision-making problem. Systematic selection of the best material for a given application begins with properties and costs of candidate materials. Selection of material for a particular application depends on material properties as well as cost of the material. Material selection is often benefited by the use of material index or performance index relevant to the desired material properties. That index term is important. What is that index? Performance index or quality index? Now, multi-criteria decision making problem is difficult to solve because there is criteria conflict or contradiction in criteria requirement. But somehow logically, if we can aggregate multiple criteria value into an equivalent single index, the problem transforms into a MCDM problem into a single criterion decision making problem, which is very easy to solve. So the technique of aggregation of multi-criteria into an equivalent single index, that we shall discuss. Now, for example, in the context of material selection, a thermal blanket must have poor thermal conductivity in order to minimize heat transfer for a given temperature difference. Thermal conductivity should be poor. That means if we consider thermal conductivity as one of our attributes, it should be lower is better. Okay, as less as possible. It is essential that a designer should have a thorough knowledge of the properties of the materials and their behavior under working conditions. Some of the important characteristics of materials are strength, durability, flexibility, weight, resistance to heat and corrosion, ability to cast, welded or hardened, machinability, electrical conductivity, etc. Systematic selection for applications requiring multiple criteria is more complex. For example, when the material should be both stiff and light, for a rod, a combination of high Young's modulus required, because stiff rod we require, stiffness should be high, and low density that will correspond to lightweight of the rod indicates the best material. Okay, that means if suppose we have some candidate material and our final product required is a rod that should be stiff enough, at the same time lighter in weight, uh, the material which should corresponds to highest Young's modulus and lowest density, that should be selected as appropriate material. So Young's modulus corresponds to higher is better requirement, and density corresponds to lower is better requirement. Now, depending on your application, you have to think of requirement of the criteria. I told there are some criteria whose higher values are preferred and some criteria whose lower values are preferred, and we have to select an appropriate candidate which can satisfy your multi criteria simultaneously up to maximum possible extent. Understand? So that is, multi criteria decision making is nothing but a compromise solution, searching a compromise solution. A particular alternative, an appropriate alternative needs to be selected that has to satisfy all of your requirements, multi criteria requirements simultaneously up to maximum possible extent. Similarly, again considering both stiffness and lightness, for a rod that will be pulled in tension, the specific modulus or modulus divided by the density should be considered. So modulus divided by density, we call it as performance index. Okay, that can be considered. I mean, these two properties are to be clubbed to compute an equivalent single index. Based on that, candidate materials can be ranked and best one can be selected. Reality often presents limitations, and the utilization factor must be taken in consideration. The cost of the ideal material, depending on shape, size, and composition, may be prohibitive, and the demand, the commonality of frequency utilized and known items, its characteristics, and even the region of market dictate its availability. In short, so many factors are there that has to be taken into consideration while selecting an appropriate material. Now, this represents a multi-criteria decision-making scenario and a decision-making matrix. Left side, you can see solution 1, solution 2, solution 3. Solution is nothing but alternative. We can see we are having 3 candidate alternatives, and you can see each alternative is being evaluated by means of 4 different criteria. Criterion 1, criteria A, B, C, D, and the last column is important where it is written total benefit. This is nothing but performance index or single index, which represents aggregation of values of criterion A, B, C, D, just to convert a multi-criteria decision making matrix into a single criterion decision making matrix. Now, based on requirement of the total benefit, we can select the best solution or best alternative and rank the solutions as per their performance. Okay, that is called ranking order of alternative solutions. and you can see criteria weights are there. Criteria weight is nothing but priority weight. According to the decision maker, someone can give higher priority weight to criteria A. Someone may give some low criteria to criteria B. So depending on application of the product, if it is product selection and alternatives are nothing but different materials, depending on the application area of the product, you can choose, I mean, you can set fix different weightage to different criteria. But the summation of all criteria weight should be equal to 1, as far as we are talking about multi-criteria decision making considering objective data, numeric data. Now this matrix represents a material selection problem. You can follow the left side, the column material is written 1, 2, 3, 4 up to 8. So we are having 8 alternatives, are nothing but 8 different types of materials. And in the second row, you can see a set of criteria are there. D represents density, C represents compressive stress, UT represents ultimate tensile stress, SB represents spring back index, BF bend force index, etc., etc. Okay, so 8 candidate materials are to be evaluated based on different criteria. Our objective is to select the best material amongst these 8 or rank the material based on their performance. And you can see at the below, material names are also specified. For example, material 1 copper to beryllium cast, material 2 copper cobalt beryllium cast, like that. Now you follow the attribute values. All are numeric, means exact numeric score is available. So it's a nothing but multi-criteria decision making problem, and the data is objective in nature. Now to solve a multi-criteria decision making problem into an equivalent single criterion decision making problem, we have to aggregate multi-criteria values into an equivalent single index. Understand? Multi-criteria values we have to aggregate in such a manner so that we can arrive as an equivalent single index, just similar to multi-objective optimization problem. In general, multi-objective optimization problem, several objectives are there. We aggregate multiple objectives and convert into an equivalent single objective function, and to solve it. Similarly, in multi-criteria decision making problem, first we have to aggregate multi-criteria values into an equivalent single index so as to transform the MCDN problem into an equivalent single criterion decision making problem to facilitate decision making. Okay, now that what we call in the previous slide, it was called the total benefit, which is the aggregated value of multi-criteria. Okay, now question arises how to aggregate. Now follow material 1, the first row, and D value is there 8.25 for material 1, CS 560, UT 940. If we add all the entries of column 1, I mean row 1, that is for material 1, and can we tell the aggregated sum is the equivalent single index for material 1? I repeat, you follow the row for material 1 in which D value is 8.25 in appropriate unit, CS is 560, UT is 940. Can we add all values and the sum can we tell as equivalent single index? The answer is no, we cannot. Why? Now the just below the table you follow different criterion corresponds to different unit. For example, density unit is milligram per meter cube. Compressive stress unit is megapascal. Since different criterion corresponds to different unit, we cannot add. Okay, number one. Number two, there may be criteria conflict. Some criteria may require higher values and some criteria lower values. For example, if we say all property values are higher is better, but cost of the material it corresponds to lower is better. So how can we add? Okay, number three. Now range of criteria value differs from one criteria to another criteria. What does it mean? Range means maximum available value minus minimum available value. You just follow the column of density D, 8.25 for material 1, 8.65 for 2, 8.94, etc., etc. Material 8, 7.08. Out of this data means density data for 8 different types of material, maximum available value is 8.95 and minimum available value is 2.67. The difference is called range of density data. Similarly, the next column, compressive strength, maximum value available value I can see 690, minimum available value I can see 50. So the range is 690 minus 50. So different criteria corresponds to different range of available data. So these are the three challenges or three problems that we encounter while aggregating multi-criteria value into an equivalent single index towards computing an equivalent single index. What are the three challenges? Number one, unit effect. Different criteria corresponds to different unit. Number two, there may be criteria conflict. Number three, range of one criteria differs from another criteria. So because of these three challenges, it is difficult to aggregate multi-criteria values to compute an equivalent single index. That aggregation should be logical, at the same time satisfying aforementioned three challenges. So how to solve that? So that I am going to discuss. Now, transformation of a MCDM problem into an equivalent single criterion decision making problem. So, three aggregation techniques I shall be discussing. One is Topsys, second one is desirability function, third one is utility theory. These techniques can be applied to solve MCDM problem involving objective data. If it is subjective data, these techniques are integrated with fuzzy logic set theory or gray set theory or vague set theory, and you can apply in fuzzy based decision making or vague set based decision making, like that. Since these techniques are initially introduced to solve objective decision making problem, means decision making problem involving objective data, quantitative data, these are called traditional decision making technique, and these techniques have further been extended in by integrating with fuzzy set theory, vague set theory or gray number set theory to solve subjective decision making problem, means decision making problem involving subjective data or qualitative data. Then the technique will be called, if it is integrated with fuzzy set theory, it will be called fuzzy topsis, fuzzy based desirability function, like that. Now, what is your requirement or criteria requirement? I already told, before going through or before solving a multi-criteria decision making problem, you have to think what is your criteria requirement. Okay, some criteria are there whose higher values are preferred, some criteria lower values are preferred. For example, extent of product quality, if it is quantified by some particular some means, the value should be as high as possible, whereas rate of rejected part uh, while receiving some goods from a supplier, the value should be as less as possible. Lesser is better. Understand? Say for a cast product, number of voids present in a cast product, total number of total length of cracks in a machine surface, the value should be as less as possible, whereas the weld strength of weldment, a number of employee participation in a training program, the value should be as high as possible. Okay, so that is called criteria requirement, so that we have to set or define before solving the decision making task. Now come to topsis. What is topsis? Topsis is basically an aggregation technique which converts multi-criteria into an equivalent single criterion so as to transform a multi-criteria decision-making problem into an equivalent single criterion decision-making problem to facilitate easy decision-making. Now, full form of topsis is technique for order preference by similarity to ideal solution. Technique for order preference by similarity to ideal solution. Solution means alternative. Okay. Solution means alternative. A set of candidate alternative. That means from amongst a set of candidate solution, we have to select the best solution or best alternative based on some criteria. Okay. So topsis method is based on the concepts of ideal solution, ideal alternative and anti-ideal alternative, beneficial criteria and cost criteria. Okay, ideal alternative and anti-ideal alternative. What is ideal alternative and anti? Before that, let me explain what is benefit criteria and cost criteria. As per topsis terminology, benefit criteria is nothing but those whose higher values are always preferred, and cost criteria are those whose lower values are always preferred. Understand? Cost criteria means, for example, rate of rejected part, number of defects in a cast product, the value is as less as possible, lower is better. So these are called cost criteria. You can question why this terminology cost is being introduced, because everywhere we go for cost cutting, we go for searching an alternative which is cost economic. So that is why the criteria which correspond to lower is better is defined as cost criteria in topsis terminology. So benefit criteria, higher values are preferred, cost criteria, lower values are preferred. Then what is ideal solution or ideal alternative? Ideal alternative is one which maximizes all benefit criteria and minimizes all cost criteria simultaneously. Ideal solution maximizes benefit criteria because benefit criteria is higher is better. Ideal solution minimizes cost criteria because lower is better is always preferred. But anti-ideal solution is the reverse one, which minimizes benefit criteria and maximizes cost criteria. Understand? Ideal solution maximizes benefit criteria, minimizes cost criteria, whereas anti-ideal solution minimizes benefit criteria, maximizes cost criteria. So based on the decision making data, we have to define two hypothetical alternatives. One is ideal alternative, one is anti-ideal alternative. And with respect to each and individual candidate alternative, we have to measure the separation distance, once with respect to ideal solution and secondly with respect to anti-ideal solution. Okay, for example, a particular alternative, say alternative 1, so you measure the distance between alternative 1 and ideal solution. Again, you measured the distance between alternative 1 and anti-ideal solution. So corresponding to an individual alternative, you have to compute two distance measures. One is with respect to ideal solution and another is with respect to anti-ideal solution. Based on these two distance measure, you compute a relative closeness for individual alternatives. That relative closeness is nothing but the single performance index, okay, which replaces multi-criteria. And finally, based on the value of that closeness coefficient, that is single index, we can select the best alternative. So question arises, which alternative is to be selected? The alternative which is closest to ideal solution, that means furthest from the anti-ideal solution, is to be selected. Which alternative is to be selected? An alternative which is as closest distance to the ideal solution, that means furthest distance apart from the anti-ideal solution. This is supposed to be the best alternative. Understand? So below represents definition of ideal solution or anti-ideal solution. Now procedural steps of TOPSIS based decision multi-criteria decision making technique. First is response measurement. Here we call it criteria measurement because objective data we have to collect or measure criteria values so as to construct the decision making matrix. Okay, decision making matrix involving different attribute, different alternative, and with respect to individual alternative, what are the criteria value. That is called decision matrix. Then comes normalization of decision matrix, because our aim is to aggregate multi-criteria decision making data. But this aggregation encounters three challenges. One is different criteria corresponds to different unit. Second one is there may be criteria conflict. And third one, range of data for one criteria differs from another criteria. In order to overcome these challenges, the following steps are to be followed. One is normalization of decision making matrix. Decision making data needs to be normalized. Then comes calculation of weighted normalized decision matrix. Normalized value needs to be computed, multiplied with corresponding criteria weight. So priority weight may be assigned at the stage. If you're as per the wish of the decision maker, we can consider all criteria are equally important, that means equal priority weight, or as per the choice of the decision maker, unequal priority weightage can be assigned to different criteria. So there comes weighted normalized decision matrix. Then from these the values entries of normalized decision making matrix, you have to determine two hypothetical solution or alternative, which are called ideal solution and anti-ideal solution. Now, ideal solution and the ideal solution, two standards of comparison are fixed. We are having some available alternatives, candidate alternatives. Now, for each and individual alternative, you have to calculate two separation distance measure. What is the distance between the particular alternative and the ideal alternative? What is the difference between that alternative with respect to anti-ideal alternative? Now, based on these two separate distance measure, closeness coefficient or relative closeness is computed corresponding to candidate alternative. This closeness coefficient is nothing but the single index which converts a multi-criteria decision making problem into an equivalent decision making single criterion decision making scenario. So by assessing the value of closeness coefficient, you can select the best one or rank the alternatives. Now this represents mathematical formulation of procedural steps of TOPSIS. First is development of decision matrix format. The row of this matrix is allocated to one alternative and each column to one criterion. So D represents decision making matrix, and within matrix X represents data, and of course data is objective in nature, numeric, quantitative data. Now you can follow A1, A2, AI up to AM. Capital A represents alternative, 1 to IM. So that means a total we have M number of alternatives, and I is general, ith alternative AI. I varies from 1 to M. So capital A represents alternative, that is candidate solution. Here we are having M total number of alternatives A1, A2, AI up to AM. I in general, when AI is called, I means ith alternative. When I equal to 1, it represents alternative 1, that is A1. When I equal to A2, when I equal to M, that is AM. And the row wise, you can see first row corresponding to A1, X11, X12, Xij, Xin. First one, if we follow the row of AI, you can see Xi1, Xi2, Xij, etc. So what is the notation of Xij? I means alternative, J means criteria. So Xij means I first, J after. I means alternative, I varies from 1 to M. Then what is Xij? Xij represents value of ith alternative for jth criteria. Okay. Value of ith alternative. What is ith alternative? That is AI. What is jth criteria? So that is Cj. And what is the actual criteria value? Xij. Similarly, X12, what does it mean? X12 means value of criteria C2 for first alternative, that is A1. Now at the last, XMN, what does it mean? Criteria value Cn for M alternative, that is AM, and the value is XMN. Now these criteria value, first column is for criteria C1, second column criteria C2, then criteria Cj, at the last criteria Cn. So we are having a total n number of criteria. So our objective is to solve a decision making problem consisting of a total m number of alternative, and each alternative is being evaluated by a total n number of criteria C1, C2, C3 up to Cn. Okay, for a particular row means different criteria value for a particular alternative, and a column means for a particular criteria different alternative values. Understand? So next, development of normalized decision making matrix. Why this normalization is required? Normalization is required to avoid unit effect, eliminate unit effect, and number two, to bring all criteria data value in a common range. Initially, in initial decision making matrix, what we have seen, uh, different criteria corresponds to different unit. So that is why it was difficult to aggregate. And number two, criteria range of data for one criteria may differ from another criteria. These two problems can be overcome if we go for data normalization. After normalization, we can see normalized data is dimensionless, no unit. At the same time, normalized data is in between 0 to 1. So all data come into a common range 0 to 1. You may question, what about criteria conflict? Because initially I pointed out three challenges for this aggregation. One is one is a unit effect, one is different range, and second one is criteria conflict. In normalization step, we are eliminating unit effect and different range. Okay, that problem. But we shall see while we will be determining ideal solution and anti-ideal solution, we shall take care of criteria conflict. Now come to the equation of normalized decision making matrix. Normalized decision making matrix follows vector normalization. Understand? You follow the nomenclature, the value xij at cj, jth column corresponding to ith alternative ai. So ai corresponding to ai, what is the value of criteria cj? That is xij. If you want to normalize this value, what will be the corresponding normalized value? That is rij. Okay, so rij, r suffix ij, is the normalized value corresponding to xij. The equation is rij equal to xij divided by square root of, you follow, x1j square plus x2j square plus xij square plus xmj square. So that means rij is equal to xij divided by square root of sum of square of all entries in the column in which xij is located. I repeat the equation. The normalized value for xij, if we denote it as rij, rij will be equal to xij divided by root over of x1j square plus x2j square plus xij square plus xmj square. Okay, summation, addition as addition of square of all entities in the column in which xij is located. Understand? And you see along this particular column, j is fixed, I is being varied from 1 to m. Okay, x1j, x2j, xij, xmj. So that means j is fixed. That means we have to consider column wise. Wise means I is varying from I equal to 1 to m. So that is why in the equation it is written Rij is equal to Xij divided by root over of square summation of square of Xij, where I varies from 1 to m. J is fixed. That means for column wise. Another example, let us consider what will be the normalized data corresponding to x11, the first one. The notation is R11. You can follow. So R11 will be, what is that? R11 will be equal to x11 divided by square root of x11 square plus x21 square plus xi1 square plus xm1 square. Understand? The particular value divided by square root of sum of square of all entities in that particular column. So that is the equation, vector normalization equation. And you can see the equation after normalization, normalized data becomes dimensionless. It has no unit. And you can see the value of this normalized data will be in between 0 to 1. So by this step, we are eliminating unit effect and the problem that initially different criteria corresponds to different range of data. These two problems are eliminated. Now come to development of weighted normalized decision matrix. Normalized data, if we multiply with corresponding criteria weight. Okay, and the notation is V. You follow initially in general Xij. I is alternative, J is criteria. Xij means value of jth criteria for ith alternative. Upon normalization, Xij is converted into Rij, and Rij, if you multiply with weight of the criteria J, that is Wj, the notation is small Vij. You can see in the weighted normalized decision making matrix, Rij is multiplied with Wj. Wj means priority weight of criteria Cj. So we'll get Vij. Vij means weighted normalized data for jth, for ith alternative for jth criterion. Understand? And you can see how many criteria are there, a total n criteria. So summation Wj, where j varies from 1 to n, is equal to 1. So first criteria W1, priority weight. Second criteria priority weight is W2, like that. Now you follow the ND, that is normalized decision making matrix. The first column R11, R21, RI1 up to RM1. This column represents first criteria column C1 for different alternatives. The entities of this column is to be multiplied with W1 because W1 is the priority weight of criteria 1. Then we will get the second matrix, weighted normalized decision matrix, V11, V21, VI1, VM1. Similarly, in the first one, ND matrix, the second column is for criteria C2, and we consider criteria weight C2 is W2. So R12 is to be multiplied with W2, R22 is to be multiplied with W2, Ri2 into W2, Rm2 into W2. So we will get V12, V22, Vi2 up to Vm2. So like that, because each column corresponds to a particular criteria. So entities of that particular column is to be multiplied with priority weight of that particular criteria. So we'll get weighted normalized decision matrix. Then we have to determine the best solution and the worst solution. Best solution is nothing but ideal solution or ideal alternative, and anti-ideal worst solution is called anti-ideal solution or anti-ideal alternative. The notation is A plus, that is ideal alternative, A minus, that is anti-ideal alternative. A plus, how to determine A plus? By definition, ideal solution maximizes all benefit criteria and minimizes all cost criteria, and anti-ideal solution minimizes all benefit criteria and maximizes all cost criteria. Understand? So how to determine, since each and every alternative is evaluated, I mean corresponds to different criteria C1 value, different criteria C1, C2 up to Cn. So there should be some criteria value for A plus and A minus. So how to decide those criteria values? Now you see WND, that is weighted normalized decision matrix. First column is criteria C1. Second column criteria C2. Understand? Forget about other criteria. Let us consider the decision making problem considering two criteria C1, C2. First column and second column. First column represents C1 value for different alternatives V11, V21, Vi1, Vm1, and second column represents corresponding to C2, that is criteria 2, weighted normalized value for different alternatives, that is V12, V22, Vi2 up to Vn2. Now what will be the value of ideal solution, criteria value for ideal solution and anti-ideal solution? Let us consider C1 is benefit criteria and C2 is cost criteria. So what will be the ideal solution value for criteria 1 and criteria 2? So follow first column. First column is for C1. C1, what are the available values? V11, V21, Vi1 up to Vm1. Out of these values, you select the maximum value and consider as C1 value or criteria 1 value for ideal alternative. Why maximum value? Because we assumed C1 is higher is better benefit criteria. I repeat, first column is the available weighted normalized value for criteria C1. Let's say C1 is benefit criteria. That means higher value is always preferred. An ideal solution is one which maximizes benefit criteria. So out of the column values, first column, that is for C1, the maximum value you pick up and consider as ideal alternative value corresponding to criteria C1. Second column is for C2. Let's say C2 is cost criteria whose lower values are always preferred. So out of this column value, you select the minimum available value and consider as criteria 2, C2 value for ideal alternative, because ideal alternative maximizes benefit criteria and minimizes cost criteria. Understand? Then what about anti-ideal alternative? Again, we assume C1 is benefit criteria, C2 is cost criteria. So from the first column value, you select the minimum value and consider as C1 value for anti-ideal alternative, because anti-ideal alternative minimizes benefit criteria. And the second column, you consider the maximum value and set as anti-ideal value for alternative for criteria C2, because C2 is cost criteria. Ideal solution minimizes cost criteria, but anti-ideal solution maximizes cost criteria. So that way you determine all criteria values for ideal alternative and ideal alternative. You can understand in this step we are considering criteria conflict, and the ideal and anti-ideal alternatives are selected in such a way that ideal alternative maximizes benefit criteria, minimizes cost criteria, and anti-ideal alternative minimizes benefit criteria, maximizes cost criteria. That is why the notation is, you see, A plus equal to maximum of Vij, I is varying, J common, when I mean J common, and J is a set of capital J, where capital J is nothing but benefit criteria. Maximum of Vij, I is varying, J common. That means you follow the first column. First column, J is common. J is 1. That is criteria C1. I is varying. I is varying from 1 to M. That means V11, V22, VI1, VM1. Out of these values, you have to select the maximum value, maximum one, because your criteria C1 corresponds to the set of benefit criteria. If it corresponds to the set of at cost criteria, you have to select the minimal value, because ideal solution minimizes cost criteria. So this is written here. I plus equal to maximum I, maximum Vij. I is varying for a particular J. When maximum value is to be selected, when J stands for criteria, belongs to the set of benefit criteria, or you have to select the minimal value when J corresponds to the set of J prime, that is the cost criteria. And you see, for anti-ideal solution, it is just reverse. Minimum of Vij when J belongs to the set of benefit criteria, because anti-ideal solution minimizes benefit criteria, and maximum of Vij when small j belongs to the set of cost criteria. Maximum, why maximum value? Because anti-ideal solution maximizes cost criteria. So the corresponding criteria values are noted as V1 plus, V2 plus, Vj plus up to Vn plus for ideal solution. So V1 plus means first criteria C1 value for A plus, second criteria value for A plus is V2 plus, like that. And similarly for anti-ideal solution, V1 minus, V2 minus, Vj minus, Vn minus. So available alternatives A1, A2, A3 up to AM is known, and their corresponding weighted normalized criteria values are known. Now two standards of comparison, that means two hypothetical alternative A plus and A minus, have been decided, and their corresponding criteria values are decided. Now for each an individual alternative, you have to compute distance once with respect to A plus, that is ideal alternative, and with respect to A minus, that means anti-ideal alternative. So for alternative A1, you first compute distance between A plus and A1, and secondly A plus and A minus and A1. A1, A plus, A minus is common standards of comparison. With respect to this hypothetical alternative, we have to compute the distance for each and individual alternative. The distance between ith alternative and A plus is Si plus. The distance between ith alternative Ai and A minus is Si minus. And the equation is this: Si plus Si minus. Is varying from 1 to m. When I equal to 1, that means distance S1 plus means distance between A1 and A plus. S1 minus means distance between A1 and A minus. Okay, so corresponding to each and individual alternative, we have to compute two distance measure, separation distance measure, once with respect to ideal solution, that is A plus, and once with respect to anti-ideal solution, that is S minus. How to compute the distance? Question arises. Now you can consider each alternative AI is being evaluated by weighted normalized value of different criteria C1, C2 up to Cn. Similarly, A plus and A minus is also having different criteria value C1, C plus up to C minus C1, C2 up to Cn. Okay, so let us consider a particular alternative is nothing but a point in n-dimensional space with coordinate values are nothing but weighted normalized values of different criteria. What are the criteria? C1, C2, C3 up to Cn. So n-dimensional space, each alternative, not only candidate alternatives, but also A plus and A minus, ideal alternative and anti-ideal alternative, you imagine as a point with coordinates, n number of coordinates, and the values are nothing but corresponding weighted normalized values. So by using the concept or equation of Euclidean distance, you can determine these two separation distance measure. And then by combining these two separation distance measure, we determine a unique index which is called closeness coefficient or relative closeness. Closeness coefficient or relative closeness. Now how to determine? Two equations are there. One is CCI, that is closeness coefficient for ith alternative. I varies from 1 to m is equal to Si minus divided by Si plus plus Si minus. The concept of Si plus and Si minus are shown in the below figure. You see the point A plus is a point and A minus at the right hand side at one point, and in between the position of an alternative, that is AI. I can be varied from 1 to m because we are having a total n number of alternatives, and you can follow the distance between AI and A plus is Si plus, and the distance between AI and A minus is Si minus. Using these two distance measure, this formulation, first formulation, Si minus divided by Si plus plus Si minus. If we consider this formula and corresponding to individual alternative A1, A2 up to AM, you compute the closeness coefficient value CC1, CC2 up to CCM. The question arises, which alternative is to be selected? Now I remind you, this CC closeness coefficient is nothing but an equivalent single index. That is why we applied Topsis technique. I I mentioned before, TOPSIS is nothing but a aggregation technique which logically aggregates multi-criteria decision, multi-criteria values into an equivalent single index so as to transform a MCDM problem into an equivalent single criterion decision making problem. Now, initially, we are having m different alternatives and corresponding data of n different criteria. Now, by aggregating this criteria value through this technique, we arrived a unique index for individual alternative, that is CC closeness coefficient. Now, by analyzing the value of closeness coefficient, we have to select the best alternative or rank the alternatives. Okay, if we compute closeness coefficient using the first equation, now which alternative is to be selected? The alternative which corresponds to the maximum value of closeness coefficient, or the alternative which corresponds to the minimal value of closeness coefficient? Which alternative is supposed to be the best? You follow the formulation Si minus divided by Si plus plus Si minus. So which alternative is to be selected? By definition, an alternative which is closest to ideal solution, that means furthest from the anti-ideal solution, this alternative is to be selected. Now, in follow this line diagram, which alternative is to be selected? When AI is closest to the ideal solution, that means when AI point, I mean
Hello. Hello. Good evening to all of you.
Sir, good evening, sir.
Datta sir has discussed the main concepts related with multi-attribution making, and he highlighted the topsys method. And due to power cut problem, he is unable to share the last slide. Then he will share the slides to all of you. Right. Then you can refer that one. If any queries are there, you can send the mail. He will answer the queries. Right. Today we are ending this section, and tomorrow morning by 10 a.m. we will start the section. The first section is related with application of multi-function deployment as a quality improvement tool in an industry. Then tomorrow morning by 9:30 we will share the link. The section will start by 10 o'clock in the morning. And here we are ending this section today. Then tomorrow morning we'll meet.
Good evening, Santosh sir. What to do, sir? No screen, no camera is coming.
Hello.
Hello,
Hello, Jitendra sir.
sir. It is
Hello,
not
Jitendra
visible
sir.
anything, sir. Yes, sir. I
Hello.
am there.
What
Yes.
happened? Only one slide is left in the discussion of Dr. Saurav Datta sir. He will share all these slides for your reference.